This is the lab on simple machines. As you see from the motivation here, the 6 bullet points show the lever, the wheel and axle, incline plane, block and tackle, wedge and screw. These are the classical simple machines. There are a couple more, which is the gears and hydraulics. I don't have them on here because I only have the classical ones. There's a footnote why that is, because in ancient times they just couldn't be produced. So anyway, I left those two out of these here, out of this list. And if you actually look in other languages, interestingly enough, we find 6 simple machines when you look them up in English, but in other languages like French or German, you find 4 or 5, because some of them, for example, are actually a combination. The wheel and axle is actually a lever that is gently attached to a wheel. Or somebody could say, hey, the inclined plane is just a wedge, or the screw itself is just a wedge on a helical plane. Inclined plane. All right, let's get going here. So pre-lab, let's see, experiment. So these are the objectives for that. Figure out the actual mechanical advantage and what a simple machine is doing and so on. And then comes the theory part, and notice this is very, very long, because once I started writing something about one simple machine, I just couldn't stop. I had to write something about everything. So anyway, then we get to the equipment needed. It doesn't look like a lot. I will show the incline in the video. I will actually leave out the pulley system, the actual experiment, but you have to use an applet in order to do that. All right, so let's look at the data table. In the video, you will see that I have an example for the inclined plane and the block and tackle. So please follow the 2 examples closely. This, by the way, is the block and tackle setup, just a fancy word for calling it the pulley system. Okay, then you will do the, I'm sorry, not you, but I did the inclined plane in the video, so look out for this one here. Then I will skip as an experiment myself the block and tackle. I also don't have an applet for the incline, but I do have an applet, and I think it's really cool for the pulley simulation, and it really mimics what I wanted to do in the actual lab. So this one you have to do. Then the video continues. This is an actual kind of like almost industrial way of doing it. So jacking up a car in order to change a tire, well, that would be the screw being used as a car jack. And you will see there's an example in the video. For the inclined plane, I used a ramp and some heavy objects on this cart here. For the block and tackle, you can see them right here, so they're industrial sized, and I put a lot of water into this bucket here and use this block and tackle in order to pull the bucket up and see what I get. And finally, I think, the lever. So here I used a shovel as a lever in order to lift part of this armchair that you see over here. And then I have a fulcrum down here. And I think that's actually the lab on simple machines. So for the next, wow, I think it's in about an hour, I have all the videos, and at some point you also have to use that pulley simulation applet. All right, I'm going to try this in one take, which is not true because this is already my second take. So this is going to be the board that will be an incline in a moment. The board is 81 centimeters long, or 0.81 meters. I'm going to put these thingies underneath, so it's going to lift it each time by 0.02 meters, or 2 centimeters, 4 centimeters, 6 centimeters, or 0.04 and 0.06 meters. So we're going to have an incline here. And then we're going to take these 2 weights here. They're identical. They're each 500 grams. So when I put this one on here, it says 500 grams and 5 newtons. Actually, it doesn't say 5 newtons, or in this case, 1,000 grams and 10 newtons, because they didn't put the Newton scale on here. This is a scale. It's supposed to read weight and force, not just mass. Yes, the two are almost synonymous, but still there's a difference. It's odd to read force. This one here unfortunately does. The other one, I'm going to use that in a moment. In any case, I'm going to take this one here, lift these up here, and I would have to exert a force of 10 newtons and lift it over a distance, a height of 0.02 meters, and that will give me the work done by simply lifting it without the incline. Now the incline is supposed to make it easier for me, so I would have to exert less force. This is where I'm going to use the other spring scale. I'm going to tear it first though, because this will make it easier for me to pull along. Imagine that you have big beer barrels here or something else, a piano pushed up here, and that's what an incline would be for. Or a wheelchair, you know, lifting somebody in a wheelchair is going to be a whole lot harder than it is to actually have them roll up the incline or push or pull them there. So here we go. I'm going to pull these up from the bottom here, so a distance of 0.81 meters, and apparently I have to exert 3.1 newtons. There we go. All right, that was actually the first measurement. The second one, so we make the incline higher, 0.04 centimeters. And pull this one up here. And I'm measuring 3.4 newtons. And technically I'm supposed to pull it all the way up here. There we go. And then here, of course, the steeper the incline is, the more force I have to exert. You will see, on the other hand, also the more efficient it gets, simply because actually on a steeper incline there is less friction, which is what I have to work against. But of course we would, if you use an incline, you probably want to go with a shallow one. So this one here reads 3.5 newtons. And these are actually the measurements. And then my incline falls apart. So I tried pretty hard to find an incline applet that I like that applies to what I want to show, and I just couldn't. I mean, this one here is actually from PHET, Physics Educational Technologies, but it just doesn't work for me, not what I want. I can do this here, I can lift this up and down here, and this person here can push the file cabinet down, and then friction slows it down, or the person can push this file cabinet up, and there it goes. Or I can change the position of the file cabinet and do this to the person. Or he can push it into the wall there, or maybe not. In any case, it just didn't work. Didn't also do me any good if I tried to change this here to a refrigerator, and the piano is really small. That would be the coolest thing actually to show, because that's where you need a ramp, you know, push a piano up a ramp, or a refrigerator, I guess. In any case, it just didn't work for me, so we're skipping this part here. There is no applet incline. This is a great applet because it's doing exactly what I would be doing in the real experiment. It starts out like this one here, and then it has all kinds of things set up for measuring and computations and so on. As I said, exactly like I wanted in my experiment. Let me just hit the play button here. Okay, that didn't work, so let me actually increase the force here, and this is kind of how it works. But I really want to mimic my real experiment, so I'm going to reset this one here. And here's what I'd like you to do. Change to the double compound. And when you do that, notice the little hand grabs right here. This is where the spring scale would be. And this little part right here, that would be the hauling line. And if you increase the applied force, you can see this is what's called the hauling line. The other four that you see here, these are the segment lines or line segments. And That's also, in a pulley system, the ideal mechanical advantage, which by the way they have written right here. Notice it says 4 right here. I consider this one over here, by the way, the cheat sheet. All right, let me introduce you to the whole thing here. So again, I'm gonna reset all of this. So double compound, I like you to increase the load to the maximum of 10 newtons, which is 1 kilogram. I actually use the same number in my real experiment. Increase the distance to as much as you can, 0.2 meters. I actually prefer 1 meter, but I think the reason that they didn't do it is that if you were to lift this one here 1 meter, you would actually have to pull this one down the hauling line here 4 meters, and that gets off the screen. Maybe that's why they restricted it to 0.2 meters. Okay, if we left the friction at 0, then we would get perfect data and 100% efficiency, which is not the case in the real experiment. We do have friction between the segment lines and the pulleys, and of course we also have to raise the lower pulley system here, which by the way they didn't put in here as being used for the analysis, so they assume that it actually has no mass. That's a little bit off. Oh well, so let's increase the friction here, and I just use an arbitrary value of 0.24. It could be lots of things. Oh, by the way, as you can see, this one here has 2 significant figures. This actually also has 2 significant figures, okay? Notice here, right here. So this is actually 0.20, and this one too, this also has 2 significant figures. Actually kind of 3, but let's call it 2. All right, so we're going to deal with 2 significant figures all the way through here. The pulley diameter we really don't need. I think that affects actually the friction simply because they're larger, so the line segments have more contact. So we're just going to leave it at the 0.2. Then this one over here, the measurements, we're going to turn these on. And then actually it says right here only the first 5 are displayed. So if I check them all, you know, I would have to turn some off so it can show the lower ones. So let me just leave it on here. By the way, all these measurements here, I call this the cheat sheet because this is virtually what you find in my table on the real experiment as well as this applet simulation. All right, other things we could do is we could show the forces on strands here. Actually, I haven't tried that yet, so let's see what happens there. Okay, I'm not sure if I see something here. All right, oh well. Let me just reset this one here and turn it off. Haven't investigated that yet. Anyway, we could also look at it from the side or the front, but I actually do want to look at it from at an angle because here I can definitely see it has 4 segment lines. On a side view, actually 2 of them overlap, so it's hard to see, right? Also, we have 4 segment lines, and later for the triple compound, we have 6, and then for the quadruple, we're going to have 8. And if you count them, it is 8. And of course, this one that you pull on here doesn't count for the segment lines because that's the hauling line. Let me go back to the double compound. By the way, notice that the first line segment is attached to the upper pulley, and that therefore we will get an even number. Sometimes I rig it up in the lab just like that, starting at the upper pulley, sometimes at the lower pulley, at which point I actually end up with an odd number of line segments. But that doesn't matter as far as figuring out the experiment is concerned and taking the measurement. In any case, we have 4, 6, and 8 segment lines or line segments, which you will find in the table in the lab menu. Okay, let's start out with double compound. And these are the parameters that I want you to choose at all times, except of course you're gonna switch then from the double to the triple to the quadruple one as you do that for the 3 sets of data that I want you to take. All right, so let's apply a force. And so I'm going to pull this one up here, and it reads 2.965 force. By the way, I tried to pull it up higher. It doesn't get any higher. I guess they put it in such a way that it matches the friction, and as it matches the friction, the 2 forces equal out to 0. So 0 acceleration then means constant velocity. If you actually pulled it up higher, if you were able to do that, again, I wasn't able to do that, then actually the thing would accelerate. You would get faster and faster. That's probably not what you do when you are using a pulley system. You're probably trying to pull at a constant speed, which means your force has to match the frictional force to have 0 acceleration and therefore have a constant velocity. Okay, so here we're done, and we read off a bunch of numbers. So let's go over to the analysis. So I need a little bit more space here for the analysis. All right, still need to push it in a little bit here. And almost there, almost there. I guess now the experiment itself is off screen, but what can you do? There we go, that should work. All right, so I already put these parameters in here. As I said, I'd like you to keep the same parameters throughout. So 1 kilogram, which is the 10 newtons, which is over here, which you can see on the load. And then the height, the maximum height of 0.20 meters. And as I said, I like to keep this at 2 significant figures. Okay, then computing the work. And you can see these equations. If the equation is not listed here, it's over here, just off the screen, right here, I guess. Oh, shoot. Right over here. So here would be the equations. I guess I could have done that. And so you have to apply these. All right. So let me get back here. And, oh yeah, this is what I wanted to do. Yeah, push them back in here. There we go. All right. So the work without the pulleys, just lifting the thing, would be the height that it's going through, the 0.2 meters, times the weight of the load. So 10 times 0.2 is 2.0 joules right there. By the way, that's this one right here. The work output is also that what I call the work without the pulleys. And that also matches the potential energy. So this one right here, what I call the work lift, they call the work output, respectively, potential energy. Okay. The ideal mechanical advantage in a pulley system is really easy to determine. Just count the number of light segments that are supporting the weight. There were 4, so the ideal mechanical advantage is 4. That should cut down the expected effort force to 1/4 of the original. So as I'm trying to lift a load that has 10 newtons, I should be able to apply just 1/4 of that, so 2.5 newtons. Okay, that's what my spring scale should read. However, there's friction, so it won't read that. All right, the hauling part distance, notice here they wrote 0.8 meters. This makes total sense. I'm going to write it again with 2 significant figures. Makes total sense because I need to pull each of these strings here, these 4 strings right here, I need to pull them up 0.2 meters, each of them. That means I have to pull a total of 0.8 meters because that string, the last one here on the right hand side, that one is connected to all the others. So it has to pull down 0.8 meters in order to make each one of them go up by 0.2. It's all one string. Okay, so that's the 0.8 meters. Let's see. Push this out a little bit more. All right. Oh, actual measured force. Shouldn't have pulled out so much. Okay, here it is, 2.965. A little bit too much on the side of sig fig. Let's just run it to 2 sig fig 3.0, and I can't actually measure that accurately anyway in a real experiment. I mean, I can only measure to 2 sig fig with the spring scales that I have. So 3.0 newtons. And I do need that measurement from here. It needs to tell me that. That's what over here in the spring scale, right here, what the handle is grabbing on, that's what I would read off right there. All right, so let's see what else we got. Work without the pulleys then actually means me pulling with 3.0 newtons for a distance of 0.8 meters, which means I come up with 2.4 joules. That's the amount of work that I put in. That 2.4 joules matches this one here, what they call the work input. I call the work done with pulleys. Same thing. Of course, again, I rounded to 2 significant figures. Okay, the actual mechanical advantage is comparing the work done with the pulleys to the work done without the pulleys. Notice I actually had to invest more work into it because of the friction. than if I hadn't done it, but at least the pulley system made it easier for me. It cut down the expected force, respectively the actual measured force, from 10 newtons down to 2.5 or 3.0 newtons. So it makes the job easier. I'm not going to get a free lunch. It's still the same amount of work, respectively even more because of the friction. In any case, the actual mechanical advantage is being multiplied, I'm sorry, not multiplied, determined by dividing the 10 newtons here, the load force, by the applied force. So 10 divided by 3.0 comes out to 3.33333. Technically two significant figures, but for the mechanical advantage, I really like to have integers there, because you're not going to talk about a machine and say, hey, it has a mechanical advantage of 3.33. No, let's just call it 3. That's good enough. By the way, when I uncheck a few things over here, we can see, there they are, right? So here is the ideal mechanical advantage of 4, again, the 4 line segments, and then here the 3.37, and as I said, I rounded to the nearest integer, which is 3. All right, and then last, the efficiency. That would be the lift work here divided by the work done with the pulleys. If these two were equal, we would come up with 1 if we divided them, which means 100% efficiency, but we're dividing by a larger number, so we get something less than 1. In fact, we get 0.84. Notice this one over here, right? So as we divide these two, 0.84, but then we're gonna, shift the decimal point in order to get percent. So 84%, that's the efficiency for this experiment. Again, we're not getting a free lunch. In fact, we have to do a little bit more work because of friction, but at least it makes the job easier. The biggest pulleys that you see these days, I believe, is actually in shipyards where they're unloading containers from container ships, and they have these huge pulleys, and therefore the machinery has to apply less force. They still have to do the same amount of work in order to lift them and then place them somewhere, but at least the machines can do it. All right, so what you have to do now is you have to use the applet in order to complete this one here using the triple compound and quadruple compound pulley systems. But just in case that the applet is not going to work for you, I actually will record this for you. But you still would have to do the calculations. All right, so here I'm going to reset this one here from my double compound, leave everything else the same. You can click on everything here, and now switch to triple compound. There it is. And yeah, everything else stays the same, and I'm gonna apply the force. Again, this is where it actually maxed out. And we give it a little time here. In the meantime, obviously it makes sense that the line segments, there are 6 of them, also gives us the ideal mechanical advantage of 6. That much I can give away. And that as I'm lifting this here 0.2 meters, I should come up with 1.2 meters for the hauling line. In fact, it's going to show us that in just a moment, right? Oh, it is getting a little off screen here. Oh, it really goes off screen. Okay. There it is, 1.2 meters, right? And then this one here, again, you can use as a sheet. And I would have to click a few off after you read these off here so you can see the remainder. So these are the remainders, right? There's the 6. And I like you to also calculate them in the table. All right. And preferably, I like you to do this simulation here. Only if the simulation doesn't load for you on your computer, yeah, go ahead and use what I'm showing you here. All right, I'm going to reset this one here. And then click on quadruple compound, and there would be 8 lines now. Again, I'm going to push this one up. Apparently, we need only 1.6 newtons. because there are so many segment lines supporting it, so it really cut down on that. We have 8 lines supporting it, so the mechanical advantage is 8, and if I divide 10 newtons by 8, I come up with 1.25 newtons. That would be the ideal force. And I gave it a different name, right? What did I call it? The expected effort force is what I gave it the name. But of course, the applied force, the actual applied force, is larger due to friction. And in a moment, we will see that the hauling line goes down by 1.6 meters because it needs to lift each one of these 8 lines by 0.2 meters. There it is, 1.6. And again, these are actually the first 5 measurements here. So you can jot these down or use them as a cheat sheet. And then I'm going to turn these off here and you can see the remainder there. All right, that's it for this pulley simulation.